In this video, we will discuss the work done by gravitational force, and we will define the gravitational potential energy. First is we have to recall the principles of how to calculate work done by a force of a moving particle. So suppose we have this reference x and y. Now suppose the particle starts at a certain point whose mass is m and applied by force of F, and it moves from A towards B. So therefore, the particle is said to be in motion. So since there is a displacement and we have this force, then work is done on the body. Now take note that at point A we have the position vector RA, and the final position we have RB. So therefore, the change in position is a straight line connecting from initial towards the final. This is the change in position. Now, if we are asked to solve how much is the work done by the force traveling from A to B, all we need to do is to consider the path, anywhere in the path. And this particle with mass m was applied by a force F. So, the distance from that point, at any point in the curve or in the path, we have r without subscript, representing at any position. So, which means that if this particle located at this point, then r is that from the origin. So therefore, again, this is at any position where rb is the initial and rb is the final position, and that is moving from A to B. So then, tangent to this curve is our infinitesimal change in position. So this is infinitesimal change in position. Very, very small change. Take note, this is the average, or this is a change in position. But this one is an infinitesimal change. So it has an angle from infinitesimal towards the application of force. So therefore, we have the change in position and we have the force. Now, taking the dot product of that is work done. So the work done by the force is the integral, because this is differential. From initial, which is RA, towards the final, it is F dot dr. Now, take note again, this is scalar quantity, and it has a unit of joule or big letter J. And take note, 1 joule is 1 Newton meter. So, scalar means there is no direction, but take note, we have 0, we have negative, and we have positive value. It's because of the direction of the force from the displacement. Okay. Now, consider an object. Consider an object. Take note that we will determine the work done by gravity. So, if there is no other force applied to this object whose mass is m, then most probably this object will move downward because of the force acting on the Earth, on that object. So, a certain reference line, let us say y is equal to 0, where upward is positive, downward is negative from this line. So, therefore, this object is in the position of positive y1. Okay? Now, take note now we have the weight. The weight is the mass times gravity, or this is the force that the Earth exerts on that mass. So, therefore, this object moves downward in the direction of the weight. Okay, so it starts from initial and we have the final position. The final position is positive y2 because again this is above the reference line. At the line again is 0. So therefore, the particle moves from y1 towards the position y2. Take note, this is RE and this is RB. Okay, so we have the change in position as y2 minus y1 because it is final minus initial. But remember that y1 in number is less than compared to y2. So therefore, this change is actually negative. Why negative? Because this is moving towards the direction of the, or towards the reference line. Okay, so therefore, take note that we have this force, the weight, and we have the displacement. So therefore, work is done on the object. But that work done is due to gravity. We call that as work done by gravity. So the question now is, what is now the relation of the, how to compute the work done by gravity in terms of gravitational potential energy? So to answer is, we will consider the general formula for the work done. The integral of the force that change in position dr ranging from RA to RB. So in this case, we are looking for the work done by the weight, and this is work done by gravity. So therefore, the force should be the mass times the gravity or the weight. But take note that that product means it is cosine. So the angle, take note, P is the angle from the displacement towards the force. Okay? So in this case, our force is the mg. Okay? Our force is mg. And the angle is what? What is the angle? Okay? And the limit or the initial is y1, while the final is y2. Okay? So at any point in the travel from y1 to y2, let us say at that point, we have the weight, because the weight does not change. Remember, weight is the force, and this is approximately the same for a certain distance from the surface of the Earth. So at any point along the travel, call this as r, or this is y, okay, position. So we have the dr or dy, okay, meaning this is an infinitesimal change. So the angle between them, look at this, because we are looking for the value of what? Of P. And this P is 180 degrees. Why? Because the weight is downward and the infinitesimal change of position is towards the positive. So therefore, and take note, again, this is reducing position. So therefore, the angle should be in opposite. Or this is straight angle, which is 180 degrees. And F, remember, is what? This is the weight, and this is mass times gravity. So the weight is mass times gravity. So therefore, we have these results. Okay, we have y1 from y2, and we have this mg cosine 180 degrees. By the way, this should be what this dr is actually the change this to dy. This should be dy because we want to know along y-axis only. R represents x, y, z components, but in this case, we have only one component, and it is the y-axis. Okay? So, again, this is dy. Okay, so therefore, what is cosine 180 degrees? This is negative 1. So therefore, and take note, m is constant. It won't change if we integrate this one. So m and z constant, cosine of p is constant. So therefore, what we have now is we have mj. Again, this is y. This is y. So change this to y, where y ranges from y1 to y2. Or you can say it r. And this is r1, this is r2. So nothing to worry. So therefore, again, the integral of mg cosine 180 degrees dy or dr is just mg negative for the cosine 180, and we have r or y from y1 to y2. So therefore, this is the initial and this is the final, upper limit and the lower limit. Okay, so therefore, applying the limit, boundary limit, it will produce a negative. So upper, it should be y2 substituted here. So mg y2 and minus mg y1. This is on how to evaluate the limit of the integral. So therefore, we have this result. Now remember that this is mass, and this mass gg, and this is y2, y1. This is final position and the initial position. So therefore, they are almost the same except the subscript. Okay. Now we have the definition of mgy. Now the definition the definition of gravitational potential energy is actually mgy, or sometimes call this as mgh. H for the height. Y is also for the height. So we have this mgy2 minus mgy1, which means that this term is actually the gravitational potential energy. And we use the symbol U. Big letter U corresponds for the potential energy. So this is, because this is subscripto, so therefore this should be U2 and this is U1. Or the final kinetic potential energy, and this is the initial potential energy. Okay? Remember, this is energy. So therefore the unit should be in joule or big letter J. And this is again, because energy, it is a scalar quantity. So again, there is no direction because this is a scalar quantity. Remember, we have the positive energy and we have the negative energy and we have the zero energy. Why? Because it is because of the height. So therefore, remember, mass times gravity times height equals the gravitational potential energy, which means that gravitational potential energy is possessed by height, vertical displacement of the particle. Because take note, this is talking about gravity. So there's no involvement about x. This is only one directional and it is along the y-axis, or this is in a vertical from the surface of the earth. Okay, the question is, when will be the potential energy be zero, be positive or negative? Okay, so consider this reference line. Again, the reference line is used in order to produce what? To produce the height. Without the reference, we cannot identify what is your height. So, the only way that we can have the height is to have the reference line. So, let us say this is a datum or a reference line. Now, we have this object whose mass is m. Take note, because of the mass, we have the weight. And weight is mg. So again, this particle will move downward. Why? Because the reference is below. And the tendency of the object is to move downward. So in that case, our y is positive. So if you substitute this positive y1 here, the potential energy at this point is positive. Why? Because mass is always positive. Gravity is considered to be as a positive because it is downward. It is the same as the force. So therefore, the only way that we can say that what's the unit of the energy, it's because of it depends upon the unit of and the value of y. Since y is positive, then we have the gravitational potential energy positive. So what is the meaning of positive potential energy? The meaning is the particle is moved towards the reference line. Okay? The particle moves towards the reference line. So therefore, we need to say that the energy is keep on decreasing. Why? Because this y is positive. So therefore, this is keep on decreasing until at the reference line y is 0. So that the energy is keep on decreasing until what? So therefore, at the reference line, the energy is 0 because y is equal to 0. Now, what will happen if this will move below the reference line? So, if it's below the reference line, then our height is a negative value. Okay? So, if you substitute this negative value to the formula for the definition of the gravitational potential energy, our energy this time is negative. So, this is negative mgy. So, what's the meaning of negative? Therefore, if you have the energy of negative, it means to say that the particle moves away from the reference line. If it is positive, the meaning is your energy the particle is moving towards the reference line. Another thing is, if we have the positive, uh, positive energy, it's meant to say that when you release it, the energy is keep on decreasing its magnitude. While the negative energy means the energy is keep on increasing in magnitude, but it is a negative sign. Okay, so that's it for the definition of the gravitational potential energy. And going back to this result, take note, we are looking for the work done by gravity, W sub Z. And previously, we have this result, negative mgy2 minus mgy1. So replace this in terms of energy. U, remember, is mgy, and we have this mgy2. So therefore, this should be y2. While this one minus mgy1, this should be u1 corresponds for the initial gravitational potential energy, and this one is the final potential energy. So the result now becomes work done by gravity is quantity U2 minus U1. U2 minus U1. But take note, this is final and this is initial. In physics, final minus initial, or in mathematics, is a kind of change. So therefore, we can say that the work done by gravity is a negative change in gravitational potential energy. Okay, so what's the use of this? The use of this is we can calculate the work done by gravity if we have the change in gravitational potential energy. And change means final potential energy minus initial. Now, what is potential energy? Definition says it is mgy. So the requirement of producing work done by gravity is we need the position 1, position 2. And take note, we need the mass and we have the gravity as the constant. Now remember, the position can be obtained only if we have the reference line. Without the reference line, we cannot we cannot measure the gravitational potential energy. Okay, so work done by gravity is a negative change in potential energy. Okay, so this is for gravity. Now take note that we have another potential energy. We have the elastic. Okay, we have the electric potential energy. So the question is this formula applicable to all potential? Answer is yes. Okay, so but take note, we derive this using the gravitational force. That's why we call this as work done by gravity. So for now, if you are asked how much work done by gravity, say it, a negative change in potential energy. Okay, now in order to apply the formula we derived that the work done by gravity is a negative change in potential energy, consider this plane. This is an inclined surface, inclined at an angle of 20 degrees, whose length is 10 meters of the inclined plane, and this is frictionless, which means that there is no friction between the contact if we place an object. The object is 15 kilograms, and this starts from rest and it moves downward. Okay, so the question is, calculate work done by gravitational force on the block. So how much is the work done by the block? Now remember that this object starts here at initial at the upper end of the incline, it ended at the lower end of the plane. How much is the work done by gravity of the 15 kilogram object in the length of 10 meters, inclined at an angle of 20 degrees, and the contact is frictionless? Okay, so to answer this question is, we need this formula we derived previously. Work done by gravity is a change in potential energy. What is again change? Change means final minus initial. So it should be written in this form, U2 minus U1. The question now is, how much is the initial? U1 means the initial potential energy. It should be at this point. And this U2 is at the lower part of the plane. So what is U1 and what is U2? Or what is the gravitational potential energy initial and what is the gravitational potential energy final? It should be the position of the block at the lower end. Okay, so to answer is we need to have the definition of the U or the gravitational potential energy. Remember, what is U? U is mgy or mgh. Okay, now in order to provide the energy, we need reference line. Take note, it should be horizontal line. Why? Because we are concerned with the vertical. So perpendicular to this line is already our y or height. So we call this as the reference line. And remember that in the reference line, y is equal to 0. Above this line, y is positive. Below is y is negative. Okay, now question. Is it always necessary that we will place the reference line at the lower part of the inclined plane? The answer is no, not necessary. You can place the reference line anywhere. When we say anywhere, it can be placed on the upper end or maybe below, beyond the lower end of the inclined plane. As long as you have a known distance from that point towards your deciding reference line. Okay? But wise move, you have to choose the lower end. Why? Because if you choose this one, your U2 final is 0. There is no energy at the lower end. And our Y is positive. If you place the reference line above, okay, U1 is 0, but your Y should be in negative. Sometimes working with negative is uh, makes difficult, but again, you can use any of that. So for now, we have this reference line at the lower end of the inclined plane. So therefore, this is y1 is this height. Okay, so we need this height. So the question is, can we calculate this height from here towards the initial? The answer is yes. Why? Because this is a right triangle. This is the hypotenuse of the triangle. We have these sides, two sides, and this angle is 20 degrees. And take note, this should be 90 degrees. Why? Because the reference line is always horizontal, while this one is vertical, so this should be 90. So therefore, this is a right triangle. Now using the sine function, in a SUKATUA, this is opposite over hypotenuse. Opposite means, over hypotenuse means sine. So therefore, we can easily calculate y1. So nothing to worry. Everything was given. Now, what is y2? Y2 is 0. So therefore, if y2 is 0, then it follows that the final, this is the final, remember. So u2 must be 0 also. So what we have now is we have this u1. But take note, minus, and this is minus. So if you do it, okay, this is 0. So therefore, this will leave us as a positive value u1. So therefore, if you ask how much is the work done by gravity, if you release freely or start from the upper going to the lower limit or lower level, so therefore it is the same as the energy at the top. Okay, because there's no energy at the bottom. So therefore, if calculating the energy above is our work done by gravity at the same time. So what is U1? U1 is mgy1. Okay? So take note, our mass is 15 kilograms, our gravitational acceleration is 9.81 meter per second squared. And what is y1? Y1 is 10 sine theta, opposite over hypotenuse, diagonal product, solving for y1. Y1 is 10 sine 20 degrees. Okay? So then, substitute everything. And this is 3.42 meters. So therefore, substitute the mass 15 kilograms, the acceleration due to gravity is 9.81 meter per second squared. The y1 is 3.42 meters. Using your calculator, we come up with a result. Work done by gravity is equal to 503.25 joule. This is the answer to the problem. Okay. Now, there is another method of calculating work done by gravity. Take note, in video number 1, work done by force. Okay, work done by constant force is work is F is cosine P, where P is the angle from the displacement towards the applied force. So the question is, can we use the formula for the work done by constant force? The answer is yes. Why? Take note that our force is gravity. Okay? Gravitational force. And it is approximately the same because the activity is within the range of the Earth's surface. So therefore, we can treat the work done by a constant force. So therefore, we can calculate another way. Another method of calculating work done by gravity. Okay. Remember, this is work done by gravity. Previously, we calculated 503.25 joules. Okay. Remember this answer. So, another solution is use the formula. This is work done by a constant force. Constant force, which means that this force didn't change. Okay. So, since we are looking for the work done by gravity, F should be the weight. S should be the displacement, which is 10 meters. And the angle P is what? Okay. The angle P is what? Okay, that's the... In order to answer what's the angle P, we need to overlay the Cartesian, where one axis should be lying along the displacements. Okay, so this should be placed along the displacement so that there's no... Okay, we can identify so that this will be our displacement line, and the angle should be coming from... Take note, this angle means this is the angle from the displacement towards the force. So it is right thing to do to assign one axis to be in the direction of the displacement. Perpendicular to that, call it as y. Okay. Now, take note, we have only... Because we are looking for the gravitational potential energy, or work done by the gravitational potential energy. So therefore, we need to focus on the what? On the weight of the object. So on the weight of the object, call it as W. Okay. This is always vertically downward, which means that since this is lying on the inclined plane of an angle 20 degrees, so the angle from this axis towards this weight is also 20 degrees. Okay. So, looking at this again, this is the formula for a constant force. So, therefore, we will replace this force with weight, and this displacement is our for 10 meters. And this angle should be identified. What is P? Is it 20? Or is it another way? Another value. Okay, look at this one. So, again, this is 20 degrees. This is why? Geometry says, if this is 20, this is also 20. Okay? Which means that if this will reduce from 20 to, let's say, 10, this will become 10. If this is 0, this will be 0 also. Okay? So therefore, take note, the question, where is your P? Your P is the angle, remember this, the angle from the displacement towards the force. In this case, this is our displacement. And where is our force? This one. Okay? And take note, this is in a clockwise direction. Clockwise direction is negative. So there are two angles. We have the positive angle in a counterclockwise, or you can use the clockwise. Both of them provides the cosine of that the same. So if this is 20, therefore this should be the complement of 20. And the complement of 20 is 70. So therefore, your P is negative 70. Again, negative because this is clockwise direction. The standard angle, positive, should be moving from X towards the in a counterclockwise direction. So therefore, we can use what's negative 70, or you can use 180, 270 plus 90, 290. Okay? Oh, no. Okay. 200, this is 180 to 70 plus 20, 290. So, the cosine of 290 is the same as the cosine of negative 70. Okay, we will choose 70. Okay, then substitute. Weight, remember, is mg. The mass times gravity is weight. Displacement still displacement. And we have the cosine of 70. Okay, so, take note. Reduction formula. The cosine of an angle, negative, is the same as the cosine of positive. Which means that if you calculate this one, any angle, the result is a positive value. So, don't worry with the negative. You can replace, you can see this as, what's that? It is a positive angle. You can treat that as a positive angle. Okay, so therefore, substitute the values, 10 for the mass, kilograms, the 9.8 for the gravitational acceleration, displacement is 10, and the cosine of 70 negative. Using calculator, the answer, the work done by gravity is 503.28 joules. Look at our previous answer. The difference is not significant. Okay, so we provided two methods of finding work done by gravity. Okay, so again, the two formulas are finding the work done by gravity is work done by gravity is a negative change in gravitational potential energy. Or you can use the work done by gravity by a constant force multiplied by the displacement and the cosine of the angle. You can choose any, but the best thing to do is to remember this. Work done by gravity is a negative change in gravitational potential energy. Okay, so that's it. Thank you. See you in the next video.